All right, ladies and gents, so we continue to move through the nutrition module, and this time we are going to move through hydration, nutrient timing, and meal structure, starting with lecture number 1, water and electrolytes. So water as a fundamental nutrient. So water is without a doubt the most critical nutrient, acting as a universal solvent and medium for nearly all metabolic processes. Defining electrolytes. This is what we need to first understand about water. Water is not so much valuable because it's water, it is what it's built up of, okay? So electrolytes are minerals that carry an electrical charge when dissolved in fluid, okay? So for example, sodium, potassium, magnesium. We touched on these in previous lectures, kind of like the big three when it comes to electrolytes. We're going to look at their role a little bit deeper now. And they're essential for nerve impulse transmission, muscle contraction, and fluid balance, okay? So what we need to understand about electrolytes is their role in driving cellular pump activity. Okay, more specifically, when it comes to electrolytes, it is the sodium potassium pump, or the Na plus K plus ATPase pump. Okay, well, let's not go about calling it that. We're going to continue to call it the sodium potassium pump, right? So this is a cellular pump that actively transport ions, which is another word for electrolytes, against what's called their concentration gradient, i.e. where they stay in larger concentrations for the majority of the time, essentially moving them out of where they normally are. And this allows for the maintenance of critical electrochemical balances that are necessary for, like I said, nerve impulses, muscle contractions, and cellular volume regulation. We're going to do our best to follow through on this. We're going to go through the first 3 steps first. So the first thing that happens is sodium binding. So we have step 1, which is sodium binding. Okay, so the 3 sodium ions, which is the kind of little purple balls you see on the left-hand side of the corner there and everywhere else in the picture, but particularly the ones in the left-hand corner, from inside of the cell, okay, where concentration is low. So the concentration of sodium is lower on the inside of the cell. They bind to specific sites on the pump protein, and you can see how it starts to shape as it moves along the cell. You have to imagine this is the same cell going through a certain process. Okay. From there, you have one molecule of ATP, which transfers one of its phosphates, again, turning ATP into ADP. This is what we spoke about earlier on when it comes to creatine and the influence the creatine has on having the supply chain for ATP regulation. Here's another example of where that becomes valuable, where that becomes important. Okay. So, like I said, the pump hydrolyzes one molecule of ATP and transfers a phosphate onto itself. That phosphorylation triggers a conformational change in the pump protein. So you can see in the second part of the diagram, you can see that kind of conforming change of the pump protein. It changes its shape, okay? Now, that conformational change drives what's called sodium ejection. That sodium that's made its way into and attached on the pump protein, it shifts and it exposes the bound sodium ions to the outer part of the cell, right? And that's where concentration is higher. Right? That causes the release of the sodium into the extracellular fluid. So sodium has made its way from inside of the cell to outside of the cell. Now, that covers at least one part of the sodium aspect. We need to think about the potassium aspect. So potassium binding, right, in its outwardly facing position, its pump now has a high affinity for potassium. As sodium goes out, potassium goes in. 2 potassium ions from outside of the cell, where concentration is low, i.e. there's less potassium on the outside of the cell, bind to the pump in the absence of sodium. We then have potassium triggers the removal of the phosphate group. So it removes that phosphate that was donated by ATP previously, and then potassium is imported. That dephosphorylation, the energy that comes from that process, causes the pump to revert to its original inward-facing conformation, which reduces its affinity for potassium ions, which releases them back into the cell's interior, where concentration is high. So it's following the same kind of general step-by-step process as sodium is, just the other direction. The net result is that for every cycle powered by an ATP molecule, by a single ATP molecule, the pump moves 3 sodium ions out and 2 potassium ions in, establishing a steep concentration gradient and a negative resting membrane potential crucial for cellular function. And the reason it's incredibly important to understand this information is because this is kind of what regulates pretty much cell communication on a global level across the entirety of anatomy. And vital for understanding how the body speaks on the cellular level. Contraction, cell-to-cell communication, metabolic regulation, a lot of it all relies, nerve impulses, all relies on this pump. It relies on the process that this pump goes upon in order to send chemical signals. So when we take a deeper look at some of these aspects, look at sodium, right? So sodium is what's called the master extracellular cation. It controls that extracellular basis of electrolyte management. So sodium concentration is the primary determinant of extracellular fluid volume. And we can actually pin that back to the sodium potassium pump. We know that sodium is moving out of the cell. It's moving into the extracellular layer. And consistent intake is then crucial because erratic sodium intake leads to fluid shifts that can negatively impact physique appearance, data trends, and predictability. Because sodium is driving that extracellular management of fluid, it becomes heavily influential in the retention of fluid. as does potassium, as does essentially the concentration gradient that we just spoke about. Potassium is the master intracellular cation. Okay, so potassium concentration is the primary determinant of intracellular fluid volume. So this is the fluid being held within cell, kind of driving fullness, driving that kind of gnarly, full, crazy bursting look. The balance, which is obviously just the ratio between sodium and potassium, is what dictates fluid distribution between intracellular and extracellular compartments, which we just described within the sodium-potassium pump. That is holding water. That is clearing water. That is one of the cellular bases of shifting fluid. Then we have things like magnesium. Magnesium's role is that it plays as a cofactor. We spoke about this again in previous lectures. About 300 enzymatic reactions, so cellular reactions, rely on magnesium to work efficiently. All right. So these are the key roles, things like muscle relaxation. Again, that counters calcium. We'll look at that a little bit deeper in later hypertrophy lectures. Nerve function and improving insulin sensitivity. Okay, so the hormonal regulation of fluid balance. So this is aldosterone-mediated fluid balance. So aldosterone is a mineralocorticoid hormone, right? It's the primary regulator of sodium balance. It's released mainly via what's called the renin-angiotensin-aldosterone system. We're going to learn a little bit more about that when we get to the endocrinology section. We're going to go into the renin system. We're going to look at it pretty deep. But we're also going to explore it now. We're going to explore that kind of process by which fluid is influenced by this system, by this RAS system, okay? So we have step one is the trigger. So low blood pressure or volume or low sodium concentration is detected by the kidneys. Again, look at that low sodium concentration, that idea of a low blood pressure, low blood volume. That's kind of the trigger that is then detected by the kidneys. When the kidneys can detect that, they then release an enzyme called renin into the bloodstream. This is what gives the idea of the renin-angiotensin system, because step three in this process is angiotensin activation. Renin converts angiotensinogen from the liver into angiotensin 1, and angiotensin 1 is then converted to angiotensin 2 by ACE, which is angiotensin converting enzyme, which is primarily found in the lungs. Step 4 is aldosterone release. So angiotensin 2 stimulates the adrenal cortex, so stimulates the adrenal gland to release aldosterone. And from there, the action moves onto the kidney. So the aldosterone acts on what's called the distal tubules of the kidneys, as well as the collecting ducts of the kidneys, which increases the reabsorption of sodium, which is Na+, from the filtrate into the blood. From there, fluid follows. Step 6 is then, of course, that fluid follows, because as sodium is reabsorbed, water follows osmotically, which is increasing blood volume and pressure. The rebound effect that we can often see within this system is that aggressively cutting sodium triggers the entire cascade. Okay, when sodium is then reintroduced, that still elevated aldosterone that responded to the low blood pressure, that's responded to the low sodium concentration, is going to massively shift the regulatory rebound effect of fluid. That kind of shift in the way that your body is responding to these hormones is what brings about that kind of sluggish visual that you carry for a couple of days after you kind of really shift this system into a position where it normally isn't. So hormonal regulation via ADH, or otherwise known as vasopressin. So antidiuretic hormone, or ADH, or vasopressin, is the primary regulator of actual water balance. Okay, it's released by the pituitary gland mainly in response to dehydration or signals of dehydration. So again, step 1, we have a trigger. So osmoreceptors in the hypothalamus detect the increase in blood plasma osmolality, i.e. blood becoming too concentrated due to water loss or dehydration. So it actually picks up on that signal. Alongside that, we have baroreceptors, which also detect significant drops in blood pressure and volume. So you get the dual pathway of managing that. Step 2 is a release of ADH. So the hypothalamus then signals the posterior pituitary gland to release anti-diuretic hormone into the bloodstream. Okay, so it limits the capacity for the body to drive diuresis because it's already detecting a low availability of fluid, a low availability of water. From there, we have the renal or the kidney action. ADH travels into the kidneys and increases the permeability of the collecting ducts. So it opens the collecting ducts by inserting what are called aquaporin channels into the cell membrane. It opens up these aquaporin channels, and from there, via those open channels, water is reabsorbed through step 4. This allows more water to be reabsorbed back from the filtrate into the bloodstream, reducing the water loss in urine and helping to dilute blood plasma back towards normal osmolality. All these responses are regulatory. They're trying to fix a problem, not cause a problem. What you can often run into then is something called paradoxical retention. So aggressively cutting fluid intake triggers a long ADH release. Okay, the body recognizes that loss of fluid. Therefore, it triggers ADH. It doesn't want to drive diuretic impact, which makes the kidneys hold on to water desperately. And then the sudden reintroduction of fluids while ADH is still high can lead to paradoxical fluid retention until the system recalibrates. So these are super common things that we see that are often exacerbated by the use of things like diuretics, which drive direct action on that RAS system, on that kind of renal anatomy and that renal kind of output. That will cause massively higher likelihoods of issues with rebounding. So this fluid regulatory capacity is obviously going to influence the fluid compartments, and body fluids consistently exist mainly in two compartments. One is intracellular fluid, or ICF, otherwise known as inside cells, and then one is extracellular fluid, which is ECF, or outside cells. So for us, again, this is probably going to be quite clear, not news to anyone. The goal is to maximize intramuscular fluid, which is simply a subset of intracellular fluid, while minimizing subcutaneous fluid, which is simply a subset of extracellular fluid, again, for a full yet defined look. So looking at how that actually applies to peak week is, understanding that these intricate systems, particularly that sodium potassium pump and that kind of dictating of gradients, how aldosterone kind of manages the system, how ADH is shifting and managing water. All of these things are prerequisites for any kind of intelligent peak and any kind of manipulation. You need to understand how one influences the other if you are going to have a direct impact, or you're going to act directly upon this RAS system, be that through interventions with fluid, be that through interventions with pharmaceutical diuretics. You need to understand the process to a high level, because without mastering these principles, any attempt at kind of drying out is guesswork, and it's likely to backfire. And if you're really negligent, it could potentially be dangerous. We've all seen how commonly pharmaceutical diuretics are quite literally killing athletes. That is down to a misunderstanding of their use, of their application, and of course of their danger. All right, ladies and gents, and that brings us to the end of lecture 1 within the hydration, nutrient timing, and meal structure section. We are now going to move on to lecture 2. This is where we're going to really look at hydration and its role in driving performance and recovery mediated outcomes. Peace and love. See you in the next video. Have a good day.